designated with their specific. They can be directly specified and you can directly purchase them from the market and directly you can utilize in your applications. As I yesterday mentioned you in the part 1 that there are 5 types of V belts A, B, C, D, E and their capacity to transmit power per belt is in the increasing order. A is the least power transmitting capacity whereas E is the highest power carrying capacity has got it is. So depending upon your requirement, space size available, pulley size and weight to be put on the shafts, considering all these either you can go for, of course the economics also matters because as the belt selection goes from A to B, they are more expensive and depending on that you can purchase the required type of selective V belts and then you can utilize in your applications. See, today I would like to introduce some more concept. Yesterday in the previous lecture we have discussed how to select a V belt with the given parameters. But we didn't take the effect of tensions in the V belts. There is always a tight side tension and a slack side tension on these two. And when you consider the mass of the belt or the weight of the belt also, another tension comes into picture which is called as centrifugal tension. So this centrifugal tension along with the normal tension, tight side and the slack side, they will decide the amount of power which can be transmitted from one driver to the other driven pulley. So therefore today I would like to show you the constructional feature of the belt, cross section of the belt. Cross section of the belt. So you can see here, I have a sketch which you can see here. See, this is the cross section of the belt. See, if you look at this, the outer cover, it is made up of fabric and rubber cover, the outermost cover. The belt cross section is trapezoidal in nature and there is always going to be an included angle. This is called as an included angle 2 beta or 2 alpha. In some books they call it as 2 alpha and in some books it is called as 2 beta. Whereas T is the nominal thickness of the belt cross section, B is the width of the cross section. Inside it is actually woven, it is actually these belts are molded. Inside you will find a composite section where you will have a fabric lining again next to the layer and inside that there are steel cords which are there along the length of the belt. And after that there are what are called as rubbers. Rubber liners or rubber linings are provided at the bottom to provide the flexibility of the belt. So therefore, if you look at the construction of this, it is a wedge shaped and to match this, a corresponding pulley is going to be made here. You can see this is the total face width of the pulley depending upon the number of belts. For example, this is made for 4 belts. As you can see here, there is a small clearance. Once the wedge shape of the belt is fitted into this, there is a small clearance between the belt and the groove and there is going to be coefficient of friction which is going to be defined between the pulley and the belt. This is going to be taken here. So these are the, you can say, major dimensions which you need to specify for making the casting of the V-groove pulleys. Depending upon how many number of pulleys or belts are required, as much the face width is going to change that. Now this particular value of alpha, it ranges from 30 degree to 40 degree. Sometimes it is, some people will take it as 38 degree, some people will take 40 degree, depending upon the type of the belt, the angle varies for each one of them. Then as I just now mentioned you, there is a relation between ratio of driving tensions for V belts. If you look at this, I'll just show with the help of a small sketch. See, if you look at this, this is the V-groove pulley like this and the belt is fitted here with the cross section here. You can see this is the cross section of the belt and if you see here, there is a normal reaction on either side and this is the total reaction R which is going to be there. These are called as R1 and R1 and if you look at this, this angle, this is going to be alpha, this is going to be alpha, and this particular angle, whatever I am telling here, this is the groove angle, which is called as 2 alpha or 2 beta, depending upon the, you can say, nomenclature. Some books, they refer it as 2 beta. Some people, they call it as 2 alpha. That is called groove angle. Now, this R1 is nothing but the normal reaction between the belts and the sides of the pulley, whereas R is the total reaction in the plane of the groove. This is the total reaction in the pulley. If I resolve these forces in the vertical plane like this and like this, if I resolve them into two components, resolving vertically, what do we get? Tell me. The total R is equal to the sum of these R1 sin alpha and R1 sin alpha. So therefore, R is equal to R1 sin alpha plus R1 sin alpha, or you can say it is equal to 2R1 sin alpha. Or therefore, this R1, whatever you say, it is going to be R by 2 sin alpha. And this can also be written as R by 2 cosec alpha. 1 by sin alpha is also called as cosec alpha. So, this is what we are going to get as a normal reaction. Therefore, the frictional force, when I say frictional force, is always equal to F equal to 2 times FR1. This is what we need to find out that. So, here if we substitute this 2 into F, R1 I will substitute this as R upon 2 sin alpha. This 2 cancels, and what you get is R into F upon sin alpha. This F upon sin alpha can be written as F1 or mu1. So therefore, this can be written as R times F1, where F1 is nothing but this virtual coefficient of friction is found out by F upon sin alpha, or you can also call it as F cosec alpha. This is the way we can calculate this. Then let us come to the two tensions, the tension ratio. We will find out how to define the tension ratio. See, as I told you, when you take one pulley and another pulley here, this is connected with the help of tension T1 and T2 here. And same thing is going to be here, and the drive may be from larger pulley to the smaller pulley or smaller pulley to the larger pulley, depends upon that. So these tension ratio in the case of you can say V belts, it will be taken as tension ratio, which is the ratio of the tight side upon slack side. It is given by F theta upon sin alpha, or F1 theta. You can call it as F1 theta. This is called as the tension ratio, tight side to slack side. So this is what you can find out. In the yesterday's lecture, I was telling you that once you have selected the standard length from the catalog, we need to correct the center distance again, because initially whatever center distance you had started with, that will not be correct, because with the given diameter and a given center distance, once we calculate the length of the belt, which is not standard. So when we refer to the catalog and make it standard length, because of this, the diameters will remain same. The center distance gets adjusted. So therefore, there is a direct formula for the corrected center distance. Corrected center distance. Yesterday I told you that by using a quadratic equation, I can find out the roots, and I can find out you can say the corrected distance even. So therefore, here I am giving you the direct formula, which is going to be L by 4 minus pi d plus d upon 8 plus, this is going to be L by 4 minus pi into bracket d plus d upon 8 whole square minus d whole square upon 8. So by using this equation, directly you can calculate the corrected center distance. Now this will be the final center distance for your further calculations. See, in the case of V belts, or even sometimes in the flat belts also, once the belt is mounted on the two pulleys, a small initial tension is given before the drive starts. So that initial tension, we call it as a T naught. Let T naught is called as initial tension, which is provided artificially with the help of a tensionometer, and the relation between the initial tension and the two tensions, whatever they are there, it is given by T1 plus T2. The relation between the tight side tension and the slack side tension along with this is given by this particular equation. Suppose if we know the centrifugal tension, for example, if I know that this is sigma 1 minus sigma c, sigma 2 minus sigma c is given by e raised to f theta upon sin alpha, where this sigma c is called centrifugal stress. Centrifugal stress, and this is given by W by G into V square into, of course, you have to multiply by 10 raised to 6 to convert this into Newton per millimeter square. Whereas sigma 1 is the permissible stress, highest permissible stress in the tension side of the belt, whereas sigma 2 is the corresponding stress, tensile stress produced in the slack side of the belt. So by using this relation, you can find out the corresponding sigma 2 can be found out, provided if you know all these details. Now once we know this, I can directly use this equation for power transmitted. If I want to know the power transmitted, P is given by T1 minus T2 into a constant, I am using a small k, into the velocity of the pulley divided by 1000. This is the, you can say, formula to find out the power transmitting capacity of one belt. Okay. Now let us see what are these. This constant, this is T1. T1 is nothing but the tension on the tight side, which is given by, you can say, area of cross section. And T2 is given the corresponding stress into area of cross section. And Tc is again given by sigma c into area. These are what you can find out the three values of this. Whereas this k is a constant, please remember, this is going to be called as a constant, and the value of this is obtained by e raised to f angle between the contact, angle of contact of the smaller pulley minus 1 upon e raised to f theta s upon sin alpha. By using this formula, I can find out the constant k. So then once you find out that k, you can find out V is the velocity which can be found out by pi d n1 upon 60 meter per second, or you can also write it by pi d n 2 by 60 meter per second, where you have to substitute these two diameters in meters only, because finally the unit of velocity is in meter per second. So we need to substitute diameters in meter. This is what you have to remember. Yes. See, there are some problems where, for example, I have two pulleys which are connected like this. They are connected by the belt. Interestingly, you must have seen in the data handbook, this is a V belt. This is a V belt. This belt is V belt, but it is a V pulley. This is a V groove pulley. And on the other side, we may have flat pulley, that is flat drive. This is the flat pulley. So this is the diameter of the flat pulley, like this. So in such cases, how to find out the total maximum diameter, pitch diameter of this pulley? Because what we know is just the pulley diameter, and over this, when it comes, this is going to come, this particular belt is going to come, I need to find out the pitch line here. I have to find out the pitch line here. And then that becomes my capital D. Please remember, it is not the diameter of the larger pulley, or the flat pulley is not going to be the pitch diameter. We need to consider the mean diameter. So I'll just show you one simple example how to find out that. See, he has told that power is transmitted from a V-grooved pulley to a flat pulley, and the size of the V belt he has already given you. For example, this is the trapezium shape of the V belt. See, this is the top, which is given as W is given as 38 mm. He has given the thickness, he has given it as 25 mm is the thickness of the belt, and the smaller width here, W1, we call it as W1, this is given by 19 mm. And what we need to find out is the CG of this, because I need to first find out this X bar, that is from bottom to this, what is the CG of this location where the pitch line is passing. So the expression for, and he has given you the diameter of larger flat pulley. He has given it to be 900 mm. This has been given as 900 mm. Okay. Now we need to add this X bar to both sides. So to find out the centroid location, distance from the base to the centroid of the V belt cross section, of the V belt section, which is given by this X bar. In the figure you can see there, from here to here, what is this X bar? It is given by, X bar is given by T by 3 W1 plus 2W upon W1 plus W. So if you substitute that, 25 by 3 into bracket 19 plus 2 into 38 upon 19 plus 38. This will give you the value of X bar as 13.9. You will get that. So automatically I can find out the pitch diameter of larger pulley. Capital D is going to be now this diameter, whatever you have got, 900 plus 2 times X bar, 13.9. 2 times X bar you have to put. So this comes out to be 927.8. 927.8 is going to be considered as the pitch circle diameter, capital D. And this is, of course, already you know, this is our small d. So for the remaining calculations, this capital diameter need to be considered henceforth. Okay. So this is about some of the formulas which are coming across in this type of examples. So now let us quickly go to some interesting problem where all these matters have been already considered. Let me solve one interesting problem on V belt with considering the tensions and all this. Okay, let me show you the problem. First, let us go to the problem statement. Yesterday we have solved already 2 problems. Today I would like to solve another 2 problems which are being given here now, like this. See, the problem says a power of 60 kilowatt at 750 RPM is to be transmitted from an electric motor to a compressor shaft at 300 RPM by V belts. The approximate larger pulley diameter is 1500 mm. The approximate center distance is 1650 mm. And overload factor is to be taken as 1.5. Give a complete design of the belt drive and a belt with cross-sectional area of 350 mm square and density of 1000 kg per meter cube and having an allowable tensile strength of sigma 1, that is 2 megapascal, is available for use. The coefficient of friction between the belt and the pulley may be taken as 0.28 and assume the groove angle as 35 degree, that is 2 alpha. So you can look at the given points. Power is given, N1 is given, N2 is given, capital D is given, center distance is given, overload factor is given, area of the cross section is given, angle of groove 35 degree is given, density is given, as well as stress and coefficient of friction have been already given to you. Now let us start with our initial calculations. We know that the speed ratio N1 upon N2 is given by d by d. Since the slip is not given here, we need not have to use that slip. Directly I will find out d into N2 upon N1, which is given by 1500 into 300 upon 750, which is given as 600 mm is the diameter of the smaller pulley. So, or you can call it as 0.6 meter. This is very much useful for us while finding the velocity of this one. Now, the sin alpha is always given by d minus d upon 2c. This is the formula which is given for this. So, therefore, I want to find out 1500 minus 600 upon 2 into 1650 is the center distance he has given. So, this will give you 0.2727 radians, and if you multiply by 180 upon 5, what you will get is 15.83 degree is going to be the value of sin alpha. What you are going to get this. Now, angle of contact, what we want? Angle of contact. Angle of contact. Theta, yes, we call it as minimum smaller pulley. This is going to be 180 degree minus 2 alpha is equal to 148.34 degree, or by multiplying by pi by 180, I will get 2.6 radians. Please don't get confused with this alpha with our groove angle. See, when you look at this, okay, when you say like this, when the pulley goes from here to here, this particular whatever is there, this is 180, okay, for I am talking about larger pulley, and here this is what he calls it as alpha and alpha. That is why the angle of contact for the larger pulley is going to be 180 plus 2 alpha, whereas on the other side, when you take the smaller pulley, the belt actually comes here, this is coming here. So, therefore, if you take the contact angle 180 minus 2 alpha, these are alpha called alpha alpha. So, let us not confuse with the alpha, we can call it as beta. 2 beta is given as 35 degree. That is what we will take groove angle as 35 degree. Okay. So, now we have found out the angle of contact for this. Yes. Now, once we know this, I want to find out the tension ratio. T1 by T2 equal to e raised to f theta upon sin beta, I can call it in this case. Since it is 2 beta, what he has given in the problem, it is 35 degree, we can say beta is equal to 17.5 degree. This is going to be the value of alpha. So, therefore, if we take this e raised to 0.28 into theta 2.6 upon sine of 17.5. This will directly give me the tension ratio 11.28. This is going to be the tension ratio what we are going to get this. Then velocity of the belt we want to find out now. Velocity of the belt, which is given by V equal to, you can take any one of them, pi d1 upon 60. Pi, you have found out the smaller diameter as 6. I think it is 1500 is the RPM, or 750. Yes, 750 is the RPM divided by 60 will give me velocity as 23.66 meter per second. See, this is the belt speed, we can call it. First we are finding the velocity of the belt. This is what we are finding now. Okay, next. Once we found out that, let us find out mass of the belt per meter length. Let mass of the belt per meter length we want to find out, and it is designated as small m, and this is given by area into length into density. Please see, per unit meter means the length has to be taken as 1 meter, that is 1000 millimeter, you can call it. So therefore, when we come to this 350 millimeter square, I am converting it to meter square, and this is 1 meter, and the density has been given 1000 kg per meter cube. This all comes out to be 0.35 kg per meter. This is what we get. Now we want to find out centrifugal tension. Centrifugal tension. I have already told you what is meant by centrifugal tension, which is given by mv square, which is equal to 0.35 into 23.66 whole square. This comes out to be 196 Newton. This is called as the centrifugal tension. By virtue of the mass of the belt, when the belt is rotating at high speed, the belt has a tendency to go away from the pulley, and because of that, there will be reduction in, you can say, grip on the belt. So we need to calculate, or we need to take into account this centrifugal effect. So once we find out, now therefore the maximum tension in the belt. See, maximum tension in the belt, if I want, it is, let us say, T. It is given by the stress into the area. Whatever the stress which has been given here into the corresponding area. The stress is given 2 megapascal and the area is given 350. So altogether it will come to 700 Newton is going to be the total tension. So once we know this total tension, we want to find out the tension in the tight side and tension in the slack side. So therefore, tension in the tight side, which we call it as T1. It is always the maximum tension minus TC, which comes out to be 700 minus 196, which is given as 504 Newton. So this is going to be the tension on the tight side. And obviously tension on the tight side is always given by, because you know this ratio, T1 by T2 ratio you know. So therefore you can directly find out, by dividing that ratio you can find out what is this. So that is 504 divided by 11.28, which you have already found out. This is going to be 44.7 Newton. So this is going to be what is called as the tensions in the tight side and the slack side. Now let us find out the power transmitted per belt. Therefore, power transmitted per belt, this is given by T1 minus T2 into the velocity. This is given by watts. If you divide by 1000, it will directly give you the kilowatts. So this is equal to 504 minus 44.7 into 23.66, 10,867 watts. And as I told you, if you divide by, you can say 1000, you will get 867 kilowatts. Please remember, this is the power transmitting capacity of one belt, one B belt. Since of course, since here the overload factor is given, since the overload factor KL is given as how much? Yeah, 1.5 is given. So the belt is, naturally the belt has to be designed for, actually KL into the rated power, actual power to be transmitted, 60 kilowatt. So therefore it is 1.5 into 60, which is 90 kilowatt is actually what we have to consider for finding the number of belts. So we need to find out the number of belts considering this. For example, we need to find out the number of belts now. number of belts, N. This total power, whatever is to be transmitted, and power which can be transmitted by per belt. If I take, this will give you about 8.3 number of belts are required. Since the number of belt is going to be an integer, we say 9 belts. So this says that for transmitting a rated power of 90 kilowatt, considering the overload factor, we need 9 V belts. Of course, here in this problem, he has not mentioned about the, what you can say, the type of the belt. But if you look at the 90 kilowatt, is only possible by D type of belt or E type of belt. So therefore, obviously, we will go for D type of belt is more recommended for this particular problem. Then lastly, he has asked you to find out the length of the belt also. Whatever the length of the belt is required, that he has asked you to find out. Let us find out that. Now, pitch length of the belt first. Okay, if you go to, as I mentioned you, table 18.29 will tell you for 90 kilowatt D type is more suitable because this is very much needed. As I mentioned you, this has to be mentioned to find out the final pitch length of the belt. Now, first we will find out pitch length of the belt now. Pitch length of belt, which is given by L. This is given by pi into bracket R plus R plus 2C plus R minus R whole square upon C. This can also be written. If you substitute all this, it is coming 7.6723 mm is going to be the P belt what you are going to get this. See, as I told you, if you look at the belt size, for example, if you take like this and like this is called as nominal pitch length and this is called as this. For D type of belt, this distance is always taken as 79. See, this particular distance is called 79. Whereas what you know is all this belt completely what you know is 6723. So if I deduct 79 mm from both sides, then automatically I will get inside length of the belt. So therefore, inside length of the belt is equal to 6723 minus, together it is 79. You have to deduct this. So in the yesterday's class I have told you, in the table you will see here like this. This is the nominal inside length. And if you say A, B, C, D like this, if you see, and E here, if you take any one of the inside length and a corresponding D length, this length for D belt, the difference between this is going to be always 79. Please remember. So that means whatever length here we got it, if I deduct 79, I am going to get the inside length, what I am getting here now. So therefore, this comes out to be 6644 mm. See, this is the approximate inside length of the belt, but it is not a standard one. So if we refer to again table 18.46 and if we take the standard length, standard inside length, please again remember inside length, it will come to 6807. This is going to be the nominal inside length, which is a standard length, which is available in the first column of the table. But what we are again interested in is the pitch length. Therefore, standard pitch length, if I want, that is again L1 you can call it. I need to add 6807. I have to again add this 79. So that again once again I will get the L. So that will give me 6886. This you can definitely see. This is readily available in the column of D section. For 6807, 6886 will be directly available in the table. That yesterday I showed you. I just would like to show you again. Yes, you can see here, this is called as the nominal inside length. And this is for example, A. Yesterday I told you, the difference between this and this is always 36. In the similar manner, if you go to D section here, of course, in this table it is not there. In the next pages, you will find entries in the D section. When you compare this and this, that is D section, this value minus this is always going to be 79. For all the values, you can just find out the difference. It always comes 79. So in that way, I have found out the value of this, and with the help of this, now I am going to finalize this length. With that help of that, of course, I have to go for the corrected center distance. Because since the length has been changed, I need to go for this. That is L1 is equal to pi by 2 d plus d, or you can either express in radius or diameter, it won't matter. So if you take this as C1 as the corrected length, and once you solve, this is 6886 is equal to pi by 2, 1500 plus 600 plus 2C1 plus 1500 minus 600 whole square upon 4C1. When you do that, yesterday I have told you, you will get a quadratic equation. You will get a quadratic equation. The root of this equation, if you find out C1 is equal to minus B, that is minus 3, plus or minus root of 1793 B square minus 4AC, that is 10125 upon 2A, this is 2. So this will give me the final center distance as 1735 mm is going to be my final corrected center distance, because once we have adopted the standard belt length, so this step is very essential. Now you can maintain with this center distance with those diameters, and with the help of D type of belt, now you are able to transmit up to 90 kilowatt, can definitely transmit through this. Now quickly I will go through another problem where some more interesting calculations are already given. So let us quickly go to the fourth problem. Yes, please look at this. It's a very interesting problem where again the data has been given here. Look at this. Two shafts 1 meter apart are connected by a V-belt drive to transmit 90 kilowatt at 1200 RPM of a driver pulley of 300 mm effective diameter. The driven pulley rotates at 400 RPM. The groove angle is 38 degree and coefficient of friction between belt and pulley is 0.25. Area of cross section of the belt is 400 millimeter square and permissible stress is 2.1 megapascal. Density of the belt material is 1100 kg per meter cube. Find the number of belts required and the length of each belt. Okay. So first, as you look at this calculation, we need to find out the weight of the belt per unit volume, that is W. W need to be found out by rho into G. The rho is given as 1100 into 9.81. This of course the unit conversion need to be done. When you want to convert this into equivalent Newton per millimeter cube, if you want to do, because otherwise you will get a Newton per meter cube you will get. So then you have to convert that into Newton per millimeter cube. Then as I told you, we can find out the diameter of the larger pulley. See, the diameter of the larger pulley is D into N2 upon N1 upon N2. He already has given you the diameter of the smaller pulley, 300 into 1200 upon 400. This will give you the diameter of the larger pulley. This is 900 mm is going to be the diameter of the larger pulley. Once you get that, then find out the belt speed, which is any one of them you can take like this. So pi into 0.3 into 1200 upon 60 will give me how much? 18.85 meter per second. This is going to be the belt speed, what you are going to get that. Once you know that, then calculate the centrifugal stress. Sigma C, how it is given, tell me? W by G into V square into 10 raised to 6. I have already told you in the previous thing. In that way, if you calculate this, what you will get is this. That is about 0.391 megapascal. You will get this. This is the centrifugal tension, centrifugal stress. What you are going to get that. Then you find out the angle of contact for the smaller pulley, which is given by 2 cos inverse d minus d upon 2c. This will give you in what is called as degrees. If you multiply by pi by 180, the answer directly what you will get is in radians. So therefore, you can write 2 cos inverse capital D, just now you got it as 900 minus 300 upon 2 into center distance being 1 meter, that is 1000. You take this into pi by 180, will give you the angle of contact in radians directly. So this comes out to be 2.532 radians. Yes, this is the angle of contact. You are going to get this. Using this, now let me calculate the coefficient of friction, which is given there, but for V belts we need to consider the influence of the groove angle. Therefore, the coefficient of friction is given by F upon sine of beta or alpha, whatever you call it. Since here in this case 2 beta is given as 38 degree, the groove angle beta is given by 90 degree. Okay, 90 degree is the beta which is given. So this is given as 0.25 upon sine of 90 degree. This will give me a value of 0.768. So now you calculate theta S. This product comes out to be 1.944, because this is needed for our calculating the tension ratio later on. Now the constant, I had already mentioned you about the constant K. What was constant K? Tell me. K was given by e raised to F1 theta upon F1 theta only, of course, minus 1 upon e raised to F1 theta. This is what we had got it, correct? So if you substitute this, you will get e raised to 1.944 minus 1 upon e raised to 1.944. This comes out to be, the constant comes out to be 0.86. The value of small k comes out to be 0.86. Okay. Now we will recalculate this. Here I have already showed you all these calculations here. Then if you look at the next page, here, this is the calculation what I did for the constant K. Now let us find out power capacity. Per belt per millimeter square area. I want to find out this. This is given by V upon 1000 into bracket sigma D minus W V square upon G into 10 raised to 6. Into this, of course, K has to be multiplied. This sigma D is nothing but the permissible stress which has been given in the problem. I think it is given as 2.1 megapascal. That you have to take 2.1 megapascal has been already given to you. So with this, if you calculate, the answer comes out to be 0.03 kilowatt. Because of this 1000, directly I can find out this. That is power transmitting capacity of the belt per unit area. That is for every millimeter square area. But since the area has been already given you, so therefore power capacity of belt with 400 mm area. This is given by 0.03 into 400 millimeter square. This will give you 12 kilowatt. Total power transmitting of one belt is going to be 12 kilowatt. In the similar manner, you can now find out the number of belts required. This is given by the total power, whatever is there, and then the power per belt, whatever is there. So the total power is given. Of course, here there is no any overload factor has been not given. So I can directly take this answer, and this comes out to be 7.5. So therefore, this if you roughly approximate it to 8 belts, you can directly go to 8 belts. Number of belts required is 8 belts for this particular application. And lastly, he has asked you to find out the belt length. L, which is 2C plus pi by 2, D plus D plus D minus D whole square upon 4C. In the present, it is 1000 plus pi by 2, 900 plus 300 plus 900 minus 300 whole square upon 4 into 1000. This comes out to be 3975 millimeter. See, once again I would like to tell you here, this is of course, as far as the problem is concerned, we can end it here. But since you know the power rating, it is given as 90 kilowatt. Once again, D type of belt is more suitable for this type of application. Similarly, you can again take this as your nominal pitch length, deduct minus 79 from this, you will get nominal inside length, and again go to that table in a D section, find out what is the nominal inside length standard you see there, that you finalize that, then add 79 to that, then directly you will get the corresponding value in the below the D section. That becomes the, what you can say, the final pitch length of the belt. And using that final pitch length, once again, as I told you, you need to correct the center distance. With the help of that equation, we get a quadratic equation for C1 and then solve that. That will give me the corrected center distance. This is what we are going to get this. So I hope with the help of these 4 problems, we have cleared almost all the doubts. So I suggest you, please refer to number of books and solve varieties of problems on this, because on every varieties of problems, the approach is different. So I think I have covered almost all varieties of cases and I have given you the details. So let me quickly go through what all I have not given yesterday. Yesterday, I was mentioning about what is called as a diameter factor FB. That was for finding the DE, that is equivalent diameter DE, which was called as dP into FB. This is the equation we have used. And this FB, it depends upon the, what you call it as the ratio. That is 2.94 or something like that. Yesterday we had got it. So if you look at this, for this particular velocity ratio, this FB need to be calculated, because once we know this, we have the kilowatt rating for each belt. For example, D type, if you go for D type, it is given in the table like this. I have already showed you whatever is there. Then there you have to use this D in the denominator here, and this has to be calculated with the help of FB. See, for example, we have got here. Now look here, 1.815 to 2.948 is our velocity ratio, and anything above, if it is there, the value of FB is to be taken 1.14. Yesterday, whatever we got, the velocity ratio was slightly more than this. That's why I had picked up FB equal to 1.14. That need to be found out here, and once you find out that, you have to come back to this equation, here. This equation, whether you are in A belt or B belt, D belt, depending on that, this DE, this particular value of DE in the denominator has to be substituted by that particular factor. This is what. See, one more very interesting factor I wanted to tell you here. Look at this. This particular table, you can see here, very interesting. You can see here, if you, let us say, if you take yesterday's problem, what we did yesterday, okay. Yes. See, look at this. Yesterday's problem. What we see, if suppose imagine that you are in a field, you are very much urgently want to know, if I go for a particular you know the velocity of the belt, and you want to quickly know what one belt of A type or B type or C type, how much power it can transmit without going through all these calculations. So therefore, in the data handbook, this type of ready tables are available. For example, you look here. This table is for A belts. See that, it is for cross section A. This type of belts, tables are available for B type, C type, D and E type also. Now let us come to this first column. What is this? First column is going to be the belt speed. So if you know the belt speed, first you have to go for this. Then equivalent pitch diameter DE, whatever you calculate here, this value of DE, if you know, corresponding to that velocity and that DE, you will get that. For example, I will just take up this problem. First problem, what yesterday we solved it, DE has come to be 85.5. See, in our problem it has come to be 85.5 mm, and our belt velocity, it came out to be 5.77 meter per second, we got it. And the kilowatt rating, roughly, what we got yesterday was about 0.8796 kilowatt. This is what we got. So how to arrive at very close figure to this? For example, 5.77 can be treated as 6. Okay, 6 meter per second. Here it is meter per second. Then your 85.55. Since your 80 and 90 is there, let us go for more closer. That is 90. We go for more closer 90. It is in between here, 0.81 and 0.94. You can see that. This is the power rating. So for 80 it is 0.81. For 90 it is 0.94. You can interpolate for 80.77. Whatever is 85.5, you can easily interpolate. So roughly you will get the same answer what you got. Here we got 0.8796. Similarly, you will get almost close to that. It is in between this, and you will directly come to know what is the probable power which can be transmitted by one single A belt at a given velocity. So directly you know the power, total power. Divide this to that. Don't worry about other constants and all that. At least you will get some rough figure of whether you need 8 belts, 9 belts, 5 belts, 3 belts. All these things can be obtained from this particular table. Okay. So once we come to this, let me quickly show some of the remaining things. We have already discussed three. Look at this. This is the V groove pulley with groove angle, belt, ride out, groove depth, pitch diameter, sheave. The belt where it is fitting, the pulley is actually called as sheave. Similarly, if you take a rope drive, chain drive, and belt drive. These three drives are called flexible drives because there is lot of slip, there is lot of power, little loss of power is going to be there, but they are very suitable for large center distance transmission. So rope drive, chain drive, and belt drives are very, very common in this application. So I will just quickly go through other things. Yesterday we have discussed what are the advantages and disadvantages. I have already told you. Okay, so now quickly let us go to this. See, let us go to the advantages and disadvantages. I have already told you. This is the, you can say, drive, one of the example of the drive which I have shown you. This is the motor. Here the speed is going to be increased. If the motor RPM is more, pulley is large, and if the driven pulley is small, it is called step up transmission. That means the RPM of this is going to be considerably increased depending upon the ratio. If it is, let us say 100 mm, and if this is 50 mm, 2 times of the speed, this machine will get down here. That is what the application is there. And you can see these are the problems which we have already solved in the yesterday's. This is the table from which you can pick up the type of the belt. Below that, center distance calculations are given. These tables are given for calculation of the power per belt and as well as the nominal pitch length available, readily available. This equation has told you how to calculate the power rating of each belt and the correction factors for service factor, angle, and the diameter factors have been shown. And this is the table which I have already showed you. This particular last figure tells you about the details about the pulley details, group details, and what distance you have to maintain. These are the standard size of the pulley and the pulley dimension, how much pitch has to be provided. Everything has been mentioned here. You have to refer to this table while making the casting drawing of the pulley. This is what you have to see. So look at this. These are the, you can say, applications of the belt. This is a Ford engine where you can see from the front the number of belts are used from dynamo to the flywheel of the crankshaft and to the some other applications. This has been given. Here also you can see the complicated drive system with number of pulleys. This has been given. With this, I come to the end of this lecture series of 2 days, that is part 1 and part 2. I have already discussed you about how to design, how to select a V belt for a given application. So in the coming days, you will be learning how to design worm gears, then how to design bevel gears, and already we have put the videos concerned to that about journal bearing and ball bearing. Already they are available on the video website. Please refer to it. Please, we advise you strongly to go through some more problems and complete your sessions. Thank you very much.